So we were discussing about the demand paging or virtual memory management system, and lastly we started discussion on different page replacement algorithms. And in the last class we have seen two page replacement algorithms, that is FIFO or first in first out, and the second one is optimal page replacement algorithm. Today let us talk about the another page replacement algorithm, which is called LRU, or least recently used page replacement technique. And to discuss this LRU technique, we will take the same page trace, that is 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 1, 2, 0, 1, 7, 0, 1. So this is the page trace that we are considering for discussing about different page replacement techniques. And we have also seen that we assume that initially in the main memory we have 3 frames which are available for accommodating these different pages. Okay. So first 3 steps will remain identical with the previous page replacement techniques, that is FIFO or optimal. That is, when page number 7 is referred, I don't have any page in the main memory, so one of the free frames will be used to accommodate page number 7. Next, when page number 0 is referred, again one of the remaining frames will be used to accommodate page number 0. So the situation will be 0, 7. Next time when page number 1 is referred, again the last frame that is available will be used to accommodate frame number 1. Sorry, this will be 7 and this is 0, and here it will be 7, 0, 1. Okay. Next time when 2 is referred, I don't have any free frame, so I have to replace one of the frames. In this case, the frame which is least recently used, that will be replaced. So you find that out of these 3 frames, frame number 1, frame number 0 and frame number 7, frame number 1 is the most recently used frame, whereas frame number 7 is the least recently used frame. So we will replace frame number 7 with frame number 2, and incidentally in this case it becomes identical with FIFO algorithm. So we replace frame number 7 by frame number 2, and the situation remains like this, that is 2, 0, 1. Next time when 0 is referred, it is available in the main memory, so there is no page fault. Next time when 3 is referred, again there is a page fault, and I have to find out that out of these frames, out of the pages which are already existing in the main memory, which one is to be replaced. So you find that out of these frames, frame number 0 is the most recently used, whereas frame number 1 is least recently used. So we replace frame number 1, page number 1 by page number 3. So the situation will be 2, 0, 3. Okay. Next time when no, 0 is the most recently used. Least recently used out of these 3 pages is which one? 0 is most recent, 2 was referred before that, and the least recently used is frame number 1. So we will replace frame number 1 by frame number 3. Okay. Next time again 0 is referred, so it is existing in the main memory, there is no page fault. Next time 4 is referred, again there is a page fault, and I have to find out the frame, the page which is least recently used. Okay. So again you find 0 is most recent, 3 was referred before that, 0 was referred again, 2 out of these 3 frames, page number 2 is the least recently used page. So we will replace page number 2 by page number 4. So the situation will be like this: 2 replaced by 4, 0 and 3, they remain as it is. Okay. Next time again 2 is referred. So now we will have a page fault, but you mind you that 2 has just been replaced. Okay. So again when 2 is referred, because there is a page fault, I have to remove one of the pages, and in this case you find that page number 4 is most recent and page number 3, that is the least recently used one. Okay. So first 4, then 0, before that 3 was referred. So 3 is least recently used frame. So I have to replace page number 3 by page number 2. So I have situation like 4, 0, 2. Okay. Next time again 3 is referred, but in this case unfortunately 3 has been replaced just now, because so far page number 3 was the least recently used page. So now again I have to find out that which one is least recent. So you find that out of these 3 frames, out of these 3 pages, page number 0 is the least recently used page. Okay. So I have to replace page number 0 by page number 3. So I have situation 4, 3, 2. Okay. Next time when again 0 is referred, again there is a page fault. And you find that out of these 3 pages which are there in the main memory, it is page number 4 which is least recently used. So I have to replace page number 4 by page number 0, and the situation becomes 0, 3, 2. Okay. So I have come up to this. Next time 3 is referred, no page fault, 2 is referred, no page fault. When 1 is referred, again there is a page fault. So in this case, which is the least recently used one? Most recently used one is 2, before that we had 3, and 0 is the least recently used page. So you replace 0 by page number 1. So what we have is 1, 3, 2. Okay. Next time 2 is referred, no page fault. Then 0 is referred, again there is a page fault. And now the page which will be replaced is 2 is most recent, before that 1, 3 is least recent. So I replace page number 3 by page number 0. So I have 1, 0, 2. Okay. Next time again 1 is referred, there is no page fault. When 7 is referred, again there is a page fault. And now the page which I have to replace is page number 2, because out of these 3 pages, page number 2 is the least recently used. So I replace page number 2 by page number 7, and the situation is like this. I have page number 1, page number 0, and then page number 7. Okay. Next time when 1 is referred, there is no page fault. 7 is referred, there is no page fault. 0 is referred, again there is no page fault. 1 is referred, there is no page fault. Okay. So now you find that the number of page faults or the number of misses that you have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So accordingly, your miss ratio will be 12 by 20, and hit ratio will be 8 by 20. Okay. Now if you compare this FIFO algorithm, optimal algorithm, and this LRU algorithm, you find that in case of FIFO algorithm, your hit ratio was 5 by 20. Okay. In case of optimal algorithm, hit ratio was 11 by 20. So you have a considerable improvement in the hit ratio. In case of LRU technique, least recently technique, hit ratio is 8 by 20, which is more than that in case of FIFO algorithm, first in first out algorithm, but less than that in case of optimal algorithm. Okay. So, we will say that optimal algorithm is the best because whenever some page is replaced, it always try to find out that the page which will not be referred for maximum period of time in future that is replaced. So, that itself ensures that you will incur minimum number of page fault. Okay. In case of FIFO algorithm, we do not have any such criteria. The page which is brought in first is replaced first. Okay. So, since we are not considering any criteria, so naturally the performance of this is likely to be poor, and that is what we get. But in case of LRU algorithm, we find that the performance is better than that in case of FIFO algorithm, okay, but it is less than optimal algorithm. And we can also say that this LRU algorithm is an approximation of the optimal algorithm. Because if you study any program, any typical program, you will find that a typical program always follows certain property, and the property which is called locality of reference. And this is the property which is exhibited by most of the user programs. The locality of reference says that once some instruction or some data is accessed, the probability that the data or instruction from the same page will be accessed is very high. Okay. So, once you access a data or access an instruction from any page, the probability that the same page or data or instruction from the same page will be referred in near future is very high. And that is quite obvious, because as we have broken the logical address space into a number of pages, and we know that instructions are executed in sequential manner, unless you have a situation of a jump instruction or branch instruction or moving from one page to another page. Okay. So, if every page contains a 256 instructions, and if we assume that none of these instructions are jump instructions or branching instructions, that means starting from the first instruction in the page to last instruction in the page, all the instructions are going to be accessed in sequence, executed in sequence. Okay. So, only when the last instruction of the page is executed, then only you move to the next page. That means referring a new page which is not same as the page that has been referred last is only 1 of 256. Okay. Similarly, if you study the number of branch instructions, you find that the percentage of branch instruction in a program is not much. Okay. So, naturally, whenever an instruction is executed, an instruction is accessed from a page say P1, it is highly probable that the next instruction will be accessed from the same page P1. Okay. That means over a short interval of time, the CPU tries to access the memory space which is confined within a locality. So, that is what is meant by locality of reference. Okay. So, that is why that whenever the CPU accesses a page, then it is highly probable that the next time the same page will be accessed, and that is the property which is used in case of LRU technique. In LRU technique, we have said that the page which is least recently used will replace that page, but a page which is most recently used will retain that page in the main memory. The reason being, the most recently used page is the page which is likely to be referred in near future. Okay? But least recently used page will not be, or it is not so likely to be referred in near future. Okay. So, using this property, and you find that when I make use of this property for page replacement, this is nothing but an approximation of the optimal algorithm. In case of optimal algorithm, we have replaced that page which is actually not referred for longest period in future. And here we are predicting, in case of LRU, we are predicting that a page which has not been referred for the longest period will also not be referred for longest period in future. Okay, so this LRU technique is an approximation of an of the optimal algorithm, and we have seen that the performance in case of LRU technique is better than that in case of FIFO, but obviously it is less than that in case of optimal algorithm because the prediction is not always true. Okay, but in most of the cases the prediction will be true. So all these different page replacement techniques, we have assumed that initially we have 3 frames available for accommodating pages. If you increase the number of frames available for accommodating pages, you will find that the hit ratio will increase and the miss ratio will decrease. Okay. So if you plot the number of hits or the number of misses versus the number of frames available for accommodating the pages. So if I put it like this, the number of page faults and this is the number of frames available for accommodating the pages. You will find that you get a curve something like this. So if the number of frames available for accommodating the number of pages is less, then the number of page faults will increase. And that is quite obvious. If instead of having 3 frames, I have only 1 frame to accommodate the pages, then every time a new page is referred, there is a page fault. Okay. If I increase the number of frames, in that case, the number of page faults will decrease. Okay. And this will follow a trend like this. And here you find that there is some region, say somewhere here. If you reduce the number of frames below this, the rate of increase of page faults is very high. Whereas if we increase the number of frames beyond this, the reduction in the number of page faults is not that significant. Okay. So we should always try to maintain that the number of frames which should be available for accommodating the pages should be somewhere here. Okay. This kind of curve is called a paracore curve. Okay. And it has been found that the region here, this corresponds to, say, if the logical address space of a particular program contains the n number of pages, then this point will be around n by 2. That is half of the number of pages in the logical address space of the job. Okay. So if an user program contains 1,000 pages, and if we are able to maintain, say, around 500 frames in the main memory to accommodate those 1,000 pages, in that case, the performance of the system will be quite okay. Because if we increase the number of frames beyond that, we are not going to gain much. Whereas if you reduce the number of frames below this, then the number of page faults will increase drastically. That is, obviously, the system performance will come down drastically. Okay. So here we have found 2 quantities or 2 measures. One is the page hit ratio, one is miss ratio. So how do we define hit ratio or how do we define miss ratio? If we have total of, say, n number of page access during the lifetime of a process, and out of that n number, so I have total of n number of, say, memory access, okay, and out of this, if I find that the page which has been referred is available in the main memory in 1 number of times, so that is a hit. Okay, So, I have n1 number of hits and n2 number of miss. Obviously, n1 plus n2 will be equal to n. And in that case, hit ratio H is defined as the number of hits divided by total number of memory access. And similarly, the miss ratio is number of miss divided by the total number of memory access. Okay. So, I have these two measures, one is the hit ratio and one is the miss ratio, and we have seen that the value of hit ratio or value of miss ratio will depend upon what type of page replacement algorithm we use. Now, this hit ratio or miss ratio is also important to find out what is the effective access time or average access time of memory. Because you find that whenever there is a miss, that means the data or the instruction which is accessed is not available in the main memory. So, it has to be brought in from the secondary storage in the main memory, and secondary storage is usually slower than the main memory. Okay. So, if we say that we have two kinds of access times, I will say that TA1 is the access time of a location in main memory okay, and suppose TA2 is the average access time of secondary storage or disk. Okay. And typically TA2 is much larger than TA1. So, whenever I have a hit, in that case the data or instruction that is requested will be available within TA1 amount of time. Whenever there is a miss, in that case the data or instruction will be available within an average time of TA2. So, maximum time will be greater than TA2, the minimum time will be less than TA2. TA1 is usually fixed. This being main memory, the time taken to access any location in the main memory is usually fixed, whereas TA2 is not fixed, because this depends upon the position of the read-write head with respect to the disk. Okay. So, if the byte that you are looking for, or in case of disk it is the block, I cannot access a single byte or a single character from the disk. I have to read in an entire block of data, put that into main memory in some buffer, we will discuss that later. Okay. Then you have to filter out the required byte or the required character from that buffer. I cannot just read a single character or a single byte from the disk. Similarly, I cannot write a single data, a single character or a single byte on the disk. I have to write it into the buffer, then from the buffer the entire block has to be transferred to disk. Okay. So, this is actually block transfer time, and the block transfer time for transferring a particular block to main memory, how much time will be needed, that depends upon the relative position of the block location on the disk and the read-write head. So, this TA2 will vary widely, whereas TA1 is usually fixed. So, for this what we use is the average access time TA2. Okay. Then effective access time, whenever the CPU tries to read some data or tries to read an instruction from the main memory, will be given by whenever there is a hit, the data is available in the main memory. Whenever there is a miss, then the data has to be brought from the secondary storage into the main memory. Okay. So, we will put it this way, that T effective time will be the hit ratio multiplied by TA1 plus, because this is something similar to the probability of occurrence of the data in the main memory, plus I have to put 1 minus h, okay, which is nothing but the miss ratio m times TA2. So, this is the average or effective access time of a data from this two level hierarchy of memory. Okay. So, first level in this hierarchy is the main memory, the second level in the hierarchy is the disk. Okay. So, now find that instead of having this two level hierarchy, if always we have to work with the disk, in that case the effective access time will be TA2. If everything I have in the main memory, that is if the main memory size is large enough that I do not need the disk, I can always put the entire part of every program, the entire part of every data in the main memory, then my effective time, access time will be simply TA1. Okay. However, that is a very costly affair because we cannot go for such a big amount of main memory. At the same time, if we put everything on the disk, it is costly in terms of time because the system will be extremely slow. So, I have a compromise by having two level hierarchy of memory, the main memory and the secondary memory, and in this case effective time, effective access time will be h times TA1 plus m times TA2. Okay. So, now find that more the h is, the hit ratio is, more efficient your memory access will be. Because if hit ratio increases, m will decrease because m is nothing but 1 minus h. So, if you have increase in hit ratio, m will reduce and the effective time, access time will also reduce. So, I have a better system if I have more h is more than much more than 0. Okay. And secondly, the effective access time will also depend upon TA1 and TA2, that is obvious. Okay. Now find that for all these memory management techniques that we have discussed, that whether it is paged memory management or segmented memory management or segmented paging or paged segmentation or demand paging, whatever it is, for in all these cases for accessing any data in the main memory, I have to have actually a two-step process. That means firstly the logical address which is generated by the CPU has to be converted into a physical address with the help of page map table or segment table. Okay. Now once you convert the logical address into physical address, then only I can access that particular location in the main memory. So again in that case it may be available or it may not be available. If it is available, I have a hit. If it is not available, I have a miss. But first time I have to access the page map table or segmentation table, whichever is the case is. Okay. Now the question is, where should we place the page map table or the segmentation table? Come to simple paging technique. If we place the page map table in the main memory, then whenever the CPU generates a logical address, I have to read some location from the main memory, that is the content of the page map table. That means I have one extra memory access. So for accessing any data or any instruction from the memory, I have to have an additional memory access. That is for getting the content of the page map table. Then only I can compute the physical address and go to the actual data or actual instruction. So the system becomes very slow. Okay. So naturally the question arises that where to put this page map table or segmentation table, whatever it is, so that the access is faster. Okay. So typical choice is you put the page map table or the segment table in what is called cache memory. Okay. And we know that cache memory is much faster than main memory. The reason being, in a system we want to have as large amount of main memory as possible, okay, but not as large as disk. So if you put these things in cost wise, in that case you will find that the cache memory is most costly among all the memory devices. After that comes main memory and then comes the secondary storage of the disk. Okay. In case of main memory, the memory is usually implemented using dynamic memory. and in case of dynamic memory, the packaging density is very high. In case of cache memory, it is implemented using static memory. And you know that the disk is a magnetic device. Okay. So because the cost of cache memory is very high, I cannot replace the entire amount of main memory by cache memory. Okay. But instead what we can do is, earlier we had a 2-level hierarchy of memory system, now we can go for 3-level hierarchy of memory system. So what we can have is, between CPU and main memory, I have another level of memory which is the cache memory. And I can also put it this way, that whenever the CPU wants to access any data or any instruction, first it will try to see whether the data or instruction is available in the cache memory or not. Okay. The similar concept is extended. In case of 2-level memory hierarchy, first the CPU tries to get the data or the instruction from the main memory. If not available, then it goes to the secondary memory. Now it will first try to check whether the data or instruction is available in the cache memory. If it is not available in the cache memory, then it goes to the main memory. If not available in the main memory, then it goes to the secondary memory. Okay. So because, and if we have a situation like this, that most of the time the data or instruction will be available in the cache memory, the system performance becomes very high. Okay. So one use of cache memory will be to store the segment table or page table, whatever it is. Okay. And secondly, to store the data or the instructions which are frequently used. So if you look at the organization of the cache memory organization will be something like this. As you have seen in case of main memory, that a logical address generated by the CPU is broken into 2 components, page number and offset within the page, or segment number offset within the segment. Similarly, when we talk about cache memory, the address generated by the CPU, or in case of cache memory, it has to be the physical address, not the logical address. The address, the physical address which is generated by the CPU is again divided into 2 components. One component is called as block number. So this is block number. And the other component is word within the block. So it is similar to page number and offset within the page. Okay. So it is, we divide the address, physical address, into fields. One is the block number, other one is the word within the block. Okay. And when we talk about cache memory, we have usually 3 kinds of cache memory. One is called associative cache memory. The second kind of cache memory is called direct mapped cache memory. And third kind of cache memory is called set associative cache memory. Okay. So we'll first discuss about this associative cache memory. Okay. So in case of cache memory, what we'll assume is, we'll assume that the main memory is divided into a number of blocks. Every block is of same size. So this is main memory, which is divided into a number of blocks. Maybe these blocks are superimposed on the paging. That means every page can be divided into number of blocks. Okay. When you come to cache memory, the cache memory also contains a number of blocks of same size. Okay. Now coming to this example, if we assume that I have a machine which accepts a 16-bit address. Okay, let me consider a smaller size machine as an example. So suppose I have a machine which is having which accepts 16-bit address. Out of those 16 bits, suppose the block number contains 13 bits and the word in a block contains 3 bits. Okay. So obviously every block will consist of 8 bytes, because if I have to identify a particular byte within a block, then byte identification has to be made only with these 3 bits, and with 3 bits I can identify only 8 bytes. So every block will have 8 bytes. So when I divide this main memory into number of blocks, every block is of 8 bytes. Okay. Similarly, in the cache memory, every block in the cache memory is also of 8 bytes. Okay. Then, along with this cache memory, there is another kind of memory which is called cache tag memory. That means for every block I have to have a tag memory. Okay. So this way, if there are say 256 number of such blocks in the cache memory, I have to have 256 numbers of tag memory. So there will be 256 numbers of tag. Here this is cache. Okay. So the idea is something like this. Whenever the CPU wants to access any memory location, it generates the address, physical address. I assume that this physical address is generated after your page table reference and all these things. So once you have this physical address, then you first try to check whether the data of that particular physical address of main memory is available in the cache or not. Okay. And for that, what you do is, you simply take this block number, check within this tag memory whether any tag memory location matches with this block number or not. Okay. So in this case, since this block number contains 30 bits, so every tag memory will also contain 13 bits. Okay. So in this example, the tag memory will contain 256 locations, or there will be 256 tags. Every tag will have 13 bits. Okay. So whenever you generate an address, the CPU generates an address, the block number field of the address is compared with different tag locations. If any of the tag memory matches with this content, then it is assumed that the corresponding data is available in the cache memory, and you get the data from the cache memory. Okay. If it is not available in the cache memory, then only you have to go to the main memory, read the data, put it into cache memory, and set the tag field accordingly. Okay. And as we have seen in case of paged memory management, that for corresponding to every entry in the page map table, I have to have a valid invalid bit. Similarly, in this case also, for every tag location, I also have a valid invalid bit, which indicates whether the corresponding cache entry is valid or it is invalid. Okay. So now find that if I want to compare the block number with every tag memory, every location in the tag memory, in that case the search time will be tremendous if I go for a linear search. Then the entire aim of putting the cache memory is wasted, is lost. So what I have to do is, I have to go for some parallel search. That means this whole thing is implemented using hardware. Okay. So how do you perform the parallel search? So the parallel search will be performed something like this. Suppose this I put as cache tag memory. Within cache tag memory, I have a register. Okay. And there are a number of cache tag locations. The main memory generates an address, CPU generates an address, consisting of block number and the byte in the block. Let me put it as offset. Okay. This block number is placed in this register. So, this is a register and these are different tag memory locations. Here what I generate is what is called a match bit. And here I have valid, invalid bits. Okay. And on this side we have the cache memory. Okay. So, it is like this. You put the block number in a register in the cache tag memory. So, this is the tag memory. Okay. Now, between the cache, this register and every such tag locations, I have XOR gates, array of XOR gates. Okay. So, it is something like this, that if I take a particular, say, tag memory location, here I have this register, it is this register. What I do is, every bit of this register is XORed with the corresponding bit in the tag memory location. So, I have an array of XOR gates like this. All these XOR outputs are then passed through a NOR gate. Okay. So, this is a particular tag memory location. So, you find that if the tag memory location is matched bit by bit with this register content, in that case outputs of all the XOR gates will be 0. When all these outputs of the XOR gates are 0, output of the NOR gate will be 1. So, this output of the NOR gate will be 1 only when the content of register matches bit by bit with the content of a tag memory location. Okay. And I have similar arrangement between the register and each of these tag memory locations. So, you find the number of XOR gates that you need and the number of NOR gates. Okay. So, output of this NOR gate, what I get, that I call as a match bit. This match bit of every gate is ANDed with the corresponding valid bit. So, this is the valid bit. Okay. So, only when the match bit is 1, valid bit is also 1, then only this buffer, this is the buffer, this buffer is active. When the buffer is active, the corresponding location of the cache block, this is an entire block, is fed to a selector. Okay. And from the selector, which of the byte of the block will be selected to pass to the CPU will be depending upon the byte number within that. Okay. So, you find that I have similar such arrangement for each of these cache blocks. Every block contains 8 bytes Okay. Then out of those 8 bytes, which byte will go to the CPU, that depends upon what is the byte number within the block. And this whole thing is done in hardware. Okay. And then again we have two options. You might be knowing about L1 cache and L2 cache. L1 cache is implemented within the CPU, whereas L2 cache is external to the CPU. But I have to have all this hardware even in L2 cache. Okay. So today we'll stop here. Next day we'll discuss about other.